Can people hear me online? Any audio issues? All right, thank you. Please don't forget about test 1 tomorrow. Okay. And it's a little bit of a retro coverage of material. So this is covering section 1.3 and 1.4, okay, including Bernoulli's equation. So on chapter 1, I think my announcement had clearly written what to expect. Just 4 questions, okay, nothing dramatic. Just make sure that you don't forget. Okay, I know it's a little bit out of your schedule, so just put reminders for yourself. Any questions on this particular event? No? All right. So the last couple of lectures we've been doing 2.3 and 2.4. Okay, so far 2.3 we were solving second order homogeneous equations. We had 3 cases, but that's what we were doing. Okay, and then 2.4 we talked about the spring mass dashpot system, mx double prime plus cx prime plus kx, where m, c, k are all positive physical quantities. M is a mass, k is the spring constant, and c is the damping coefficient. Yeah. So these 2 things are pretty much yielding the same mathematical results. Okay, depending on the values of m, c, and k, there were 3 different cases, either over damped, under damped, or critically damped. So that's what we were doing on Monday and Tuesday respectively. So I hope at this stage all of you know how to solve a homogeneous second order equation. Okay, so that is the expectation at this point. So if you have any questions about that, please let me know right now before we go further. All of you okay with these things? Any questions? All right, so now we can slowly start relaxing some of the things we have been doing so far. Okay, the first thing we can relax is to look at non-homogeneous equations. Okay, so that kind of opens up a whole new can of worms, so to speak. Okay, so section 2.5, non-homogeneous still second order linear constant coefficient. Okay. Differential equations. Some of these things cannot be relaxed in general because if you make it non-linear, it just gets too wild. Okay, there is no general way to solve non-linear second order non-homogeneous equations. Okay, there is no such thing. You just have to do it on a case-by-case basis. Again, if you make the coefficients non-constant, for example, if you do x square y double prime or y square y double prime, okay, again the equation becomes too complicated. You have to then do it on a case-by-case basis. So these are the things you could do in general, and that's what we are trying to discuss here. Okay, so non-homogeneous means you're setting a y double prime plus b y prime plus cy equal to some function f of x. Okay, where f of x is some continuous function of x, so that differential equation changes its behavior based on what this is. Solving this equation is based on a very simple theorem. Okay, well, it kind of looks simple, but it's a very deep theorem in a way. If y subscript h is the solution for the homogeneous differential equation a y double prime plus b y prime plus cy equal to 0. That's what we were doing the last couple of days. So if you know this, and if y subscript p is the particular solution for the non-homogeneous part f of x. Okay. So that's a new thing here. So for the non-homogeneous then the general solution to this non-homogeneous equation I written up there, okay, the general solution is given by y of x equal to yh of x plus yp of x. And yh and yp are functions of x. That's why I put it as yh of x and yp of x. Again, this is some kind of a superposition principle. Okay, if you know individual parts of the equations solutions, you can always bring them together and write one whole function that will solve the entire equation. Okay, so we know this one from section 2.3. So depending on cases 1, 2, or 3, you could find your YH, okay, H for homogeneous. This is the one we are trying to find today. That's what our focus is. And once you have both the solutions, you can combine them together. Some textbooks also call this as the complementary solution. What is it, an I or an E here? Complementary. E, I. Not the mathematical I or E, but also called the complementary solution. So sometimes you might say some textbooks write YC, yeah, that is the same thing. Okay. All right. So the question is, how do we find this YP? Okay. Well, the answer is simple. Okay. Let's guess it. That sounds dangerous. Okay. What kind of guess do you want to make? Just a wild guess? Among all the infinite number of functions, you just start guessing? Or is there a nice way to start guessing, and if is there a rhyme and reason to what we are trying to do here? Okay. Not a wild guess. It's going to be an educated guess. There will be some guidelines about what kind of guess you're going to make, and then we will start doing some math based on that guess, and we'll arrive at the solution if you did not make any mistakes. This method is called the method of undetermined coefficients. Some textbooks also call it the method of educated guess, but it's officially called the method of undetermined coefficients because that's what we're trying to do here. Okay, there are some coefficients. There will be some coefficient or coefficients okay, depending on the problem which we are trying to find based on the equation, okay, and that is what's going to decide your YP. This thing is getting more and more resistant each day. All right. So the types of functions we are going to discuss here, okay, are of three types. So three. So this method of educated guess only works for these three kinds of functions. If there's anything else, we need different techniques. Okay. Three kinds of functions. F of x being an exponential function, okay, or some k could be positive or negative. Okay. If k is 0, there is no meaning, but or there is no point to it. Two, f of x equal to either a cosine and or a sine function. Okay. Again, k is some number. And the third one is if f of x is a polynomial of some degree. Okay. All of you hopefully know what a polynomial means. Okay. It's just the sum of terms where the exponent should be a positive integer, right? So polynomial in general looks like this. Okay. An x to the power of n plus a n minus 1 x to the power of n minus 1, where n is a positive integer. You cannot have square roots or negative exponents or other funny things going on here. Okay. That's what a polynomial means. Well, these are three typical functions that you would see in any of the mathematical applications. So this is a pretty nice class of functions. Okay. So the good thing about all these functions is that these are all continuous and differentiable everywhere. Exponential, cosine, sine, polynomial. Okay. There is no gap anywhere in the graphs of these functions. So there is no need to worry about, oh, is it going to be continuous here, differentiable here? Okay. It's one of the reasons why this method will always work for those three classes of functions. So the process of solving a non-homogeneous equation is as follows. Okay. First step is always to find the homogeneous solution, YH. That's something you've done over the last couple of days. Okay. So from section 2.3. So find YH always, because this should be done first. Don't postpone this for the last step. Okay. You will see why. 2, guess YP based on f of x. Okay. Again, I'm promising that f of x would be one or a combination of these functions. So this you could add these or multiply these, but nothing outside of these functions. And then evaluate the unknown coefficients. There's some very simple algebra there. Okay. And step 3, write y equal to YH plus YP. And if the question has initial values, just find C1 and C2. Okay. I won't be doing C1, C2 things today because we have got enough things to do today. So I'm going to keep my problems mostly general solution. Okay. In 2.6, when we do the application, there will be problems where you have to find those two. All right, so that is the process here, pretty simple. Okay. let's start with the first class of functions, the exponential function. So case 1, f of x equal to e to the power of kx. Okay. This educated guess is just based on the fact that if it is exponential, the guess should also be exponential. Okay, there is no reason to think about any other function at this point, right? We are expecting exponential function on the right hand side, so the left hand side also be better exponential. Okay, you cannot have sine and cosine here and then expect e on the right side. So you'll guess yp to be some coefficient. Okay, this is the part that you're trying to solve here, times the same exponential function. That's why it's an educated guess. Okay. What do you do then? You find yp prime, yp double prime. This is a second order equation. Okay. Plug into the differential equation a yp double prime plus b yp prime plus c yp equal to your function f of x. Now it makes sense. You have exponential, 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 exponential. Okay. So at this point, you will see that the only unknown coefficient or the only unknown term here is this capital A. Okay, and you can solve for A. Simple, right? So there is a little bit of calculus here to still know how to find derivatives. Okay, but apart from that, it's a mostly algebraic process, comparing two sides of the equation and trying to find this A. Let's do some examples. Yeah. So example 1. I mean, all of us should know that things are going to go wrong at some point. Okay. If this was this easy, then differential equations should be super easy, but you should know that it's not going to be this easy all the time. So let's start with easy examples, and then we will start dealing with dirty things. Y double prime minus y prime minus 6y. I think this factors here equal to 3 e to the power of 4x. This 3 should not affect you in any way. Okay. What you really should focus on is this term, the e to the power of 4x. Okay, that is the guiding term to decide what your guess would be. Okay, the 3 will take care of itself later. Okay, so don't worry about 3 and start making that a big deal. Step 1, find the homogeneous solution. Okay, so y double prime minus y prime minus 6y equal to 0. Hope all of you are experts in this now. So just do this quickly. R square minus r minus 6 equal to 0. Okay. So we have r minus 3 times r plus 2 equal to 0. So this is case 1. So your YH would be C1 e to the power of 3x plus C2 e to the power of negative 2x. So just keep it there, okay? So in this problem, we are just going to add it later to step 3, but in other problems, this is going to be super important when we make our guess function yp. Okay? So nothing new there, right? Step 1. Step 2. guess yp equal to a e to the power of 4x. Some students do 3a e to the power of 4x. You don't have to do that. Okay. Let the 3 stay there. We'll take care of 3 later. So let's just start with a e to the power of kx. K is 4. Yp prime is 4a e to the power of 4x. And yp double prime 16a e to the power of 4x. Now plug it into the original differential equation that was given in the question. Okay, so this is what it is: yp double prime minus yp prime minus 6yp equal to 3 e to the power of 4x. So plug in each of these there. You will see that the only term that is really standing out is this capital A. 16a e to the power of 4x minus 4a e to the 4x minus 6yp, that's going to be minus 6a e to the 4x equal to 3 e to the 4x. So that's 16 minus 4, 12. 12 minus 6 is 6a e to the 4x equal to 3 to the 4x. Cancel, cancel. And you get a equal to half. And that a is what we need. So that's why it's called the method of undetermined coefficients. You had a coefficient that was unknown. That's here. Now you can just write your general solution. Step 3. Y equal to yh plus yp. That's the superposition principle here. If you have individual solutions, each of which satisfies the equation, you can combine them together. Okay. So it's going to be C1 e to the power of 3x. Give me 1 second, okay? Just change the batteries here. Oh, that's a bad one. Start stealing batteries now. Okay, I think this one should survive. So C1 e to the power of 3x plus C2 e to the power of negative 2x plus a half e to the power of 4x. So that is your final answer. Okay, any questions on that procedure? Looks pretty straightforward. Okay. All right, let's look at case number 2. This is the one you should be a little bit careful. Okay. Case number 2 is where it is either a cosine or a sine or both. Okay. Cosine kx and or sine kx. I hope all of you have done enough calculus to know that unlike exponential functions, sine and cosine has a kind of weird behavior that if you take the derivative of sine, it becomes a cosine. And then if you take its second derivative, which is going to be the derivative of cosine, it's going to be a negative sine. Okay. Kind of flip-flops, right? It becomes cosine, becomes sine. Okay. So the first and second derivatives are not really the same, unlike an exponential function. Okay. So for this reason, you have to be careful about what yp here is. So your yp, irrespective of whether it's this or both, okay, your yp is always going to be a times cosine kx plus b times sine kx. Always. It's not a matter of choice where you pick one of them as you like. And again, the reason is because we don't know which way it's going to behave. Okay. The derivative of sine is cosine, derivative of cosine is negative sine. And since the equation has both first and second derivatives, okay, you have to account for both these functions and let it play by itself. So it's not just a cosine kx or a sine kx. Just keep this in mind. This is the only place where some students tend to forget that you have to do both and not just one of them. Okay. But the process is still the same. Just go and plug it in and solve for A and B. Okay. Same process. Solve for A and B. Out of all the problems in this section, I think the ones with sine and cosine would be a little bit lengthier because you have to find two constants. Okay, so just give yourself enough time when you do these problems. Example 2. I'm going to keep the same left-hand side because I don't want to keep doing this homogeneous solution over and over. Okay, so let's just change the right-hand side here, and let's do 2 sine 2x. All right, so the first step is still the same, okay, because I have not changed my left-hand side. The homogeneous solution is always true, okay, irrespective of what happens on the right-hand side. This is not going to change. Now let's just focus on step 2. And guess yp equal to a cosine 2x plus b sine 2x. All right, so yp prime would be negative 2a sine 2x plus 2b cosine 2x. And yp double prime, take its derivative once more. Okay, so it's going to be negative 4a cosine 2x minus 4b sine of 2x. Okay, so you can think about this, and if those coefficients were positive, you could think about this as a spring mass dashpot problem with the external force, which is what we'll be doing in section 2.6. Okay, so be careful when you're doing the next step. You're going to plug this into the differential equation you're given there. Okay. It's going to look ultra long now because you're going to write all these terms. Okay. So give yourself enough space. So I'm going to plug it into yp double prime. Hope this much space is enough. Yp double prime minus yp prime minus 6 yp equal to 2 sine 2x. That's going to be negative 4a cosine 2x minus 4b sine 2x. That is your yp double prime minus yp prime. I'll try to keep my terms kind of together if that is possible spatially, but maybe not. Minus yp prime would be minus of this term. I'm going to write the cosine first and sine second so that I could see it easily later. That's minus 2b cosine 2x plus 2a sine 2x. That is my minus yp prime. Minus 6 yp would be negative of these two terms times 6. That's going to be minus 6a cosine 2x minus 6b sine 2x. You don't have to write it in this form. Okay, just easy to see what's going on with each of these terms later when you combine these. Okay. And the right hand side is, remember there is no cosine on the right hand side. Okay, so let's, for as a space saver, okay, let's keep a 0 there. 0 cosine 2x plus 2 sine 2x. Because we are trying to match or compare the coefficients of terms on both sides. So cosine will match with cosine and sine will match with sine. Okay. All right, let's simplify the left hand side. Oh. All right, let's simplify those terms. Multiplying cosine 2x is going to be negative 10a minus 2b. And then you have 2a minus 10b sine 2x. So things are slowly getting into shape. Okay, equal to 0 cosine 2x plus 2 sine 2x. Okay. If this equation has to be true, then the cosine and sine terms should have the same coefficients on both sides. Okay. So negative 10a minus 2b should be equal to 0. Just by comparing the coefficients, because these two are the same thing, right? And similarly, we have 2a minus 10b equal to 2. So to solve a system of equations, which is not too bad because the first one, the right hand side is 0, we don't have to do anything fancy here. So this becomes b equal to negative 5a. Right? And you can plug it into the second equation and you get 2a plus 50a equal to 2. That's 52a equal to 2. So a is 2 over 52, which is 1 over 26. Assuming that I did not make any mistakes here. 10 times 5 is 50. Yeah. And b would be the negative 5a. So it's going to be negative 5 over 26. So our initial guess was right. Okay, we had to have expected both cosine and sine terms, even if the question only had one of them. Okay. So overall, the general solution now is y equal to yh plus yp, which is, okay, you should find time to write this last step. Okay, don't just find your yp and move on. Okay, you had a yh first, so it's going to be c1 e to the power of 3x plus c2 e to the power of negative 2x, and then these two terms plus a, which is plus 1 over 26 cosine of 2x minus 5 over 26 sine of 2x. Any questions on this one? So it's just raw math, right? Just need to do it. Okay. It's a bit lengthy. Out of all the three cases, I think case 2 is the lengthiest, okay, in terms of the time it takes to do it. But as long as you don't make any mistakes, it's a pretty routine problem. Okay. Now let's do the last one, which is polynomials. I'm going to erase this part here. Okay. So case 3, f of x equal to a polynomial of degree n. Well, theoretically, it could be a polynomial of degree n. When you actually do it, it could be a polynomial of degree 2 or 3 or 1. Okay, usually not more than 3. So usually n equal to 1, 2, 3. Okay. Just so that you won't go insane. So then your guess yp would be also a polynomial of the same degree. Okay. Makes sense. You don't expect an exponential function if you have a polynomial. Okay. So a polynomial of the same degree. And since we're going to focus mostly on polynomials of 1, 2, 3, let me just write those cases down explicitly. Okay. So for n equal to 1, which is a linear function, okay, the polynomial yp would be ax plus b. Okay. It's not just ax. You have to write the most general polynomial of that same degree. Okay. N equal to 2, your yp would be ax square plus bx plus c. So irrespective of how your f of x looks like, you have to write all the terms in this polynomial. Okay. And n equal to 3, yp would be ax over 3 plus bx square plus cx plus d. You can see what will happen if you have higher degrees, but those kind of becomes more academic at this point. So the crucial thing here is to make sure that you must write all these terms even if your f of x only has 1 or 2 of these terms. Okay. Maybe that is not very clear. What I mean is this: if you have, say, f of x equal to x square, okay, that's a polynomial of degree 2. Okay, that doesn't mean that you just write yp equal to ax square. Okay, that is wrong. You need to write all the terms ax square plus bx plus c. That is what I mean by saying that you should write all these terms even if f of x does not have them. Okay. The good thing with polynomials is that when you take derivatives, the degree goes down by 1. Okay. So it's not as painful as the sine cosine terms. Any questions on the polynomial case? Again, a common mistake students make is if they see only f of x equal to 2x, for example. Okay. What would be your yp? X plus b, not just ax, okay, because it's very tempting to say, oh, there is only one term here. So that is not complete. It's partially correct. Okay. The fully correct guess would be x plus b. Okay, so that is what I just wanted to keep in mind. Except that one, it's a pretty easy thing to do. So let's do a quick example. Example 3. Let's keep the same left-hand side. Okay. Y double prime minus y prime minus 6y equal to, let's just do x square. So I'm recycling the left-hand side. Okay, you don't have to do the homogeneous solution altogether over and over because we did this for example 1. It's the same thing. So let's just focus on yp. Polynomial of degree 2. General polynomial is ax square plus bx plus c. Yp prime is 2ax plus b. And yp double prime is 2a. Sometimes students make mistakes of forgetting that the derivative of a constant is 0. They keep on writing unnecessary terms and dig a hole for themselves. So the good thing is that the number of terms decreases in a polynomial. So plug it in, yp double prime minus yp prime minus 6y. Again, let's keep some placeholders here, x squared plus 0, x plus 0, so that we have something to compare on both sides. Okay. That's going to be 2ax plus b, that is my yp double prime, minus yp prime. Oh, that's the wrong term. I should look here. Yp double prime is 2a minus yp prime is 2ax plus b. Minus 6y is yp is your original guess. So it's minus 6 times ax squared plus bx plus c. Equal to 0x squared plus, sorry, x squared plus 0x plus 0. Okay. So the key thing here is to kind of distribute everything and collect the terms of the same type. Okay, so we have a negative 6a x squared that unfortunately is going to give us some fractions, but that's okay. Plus negative 2a minus 6b times x. And the last term has 3 constants, okay, plus 2a minus b minus 6 times c. And that's equal to x squared plus 0x plus 0. And it goes without saying that you start with the easiest one and solve it one after the other. Okay, so compare the coefficients of x squared, you get negative 6a equal to 1. So A is negative 1/6. Then you have negative 2A minus 6B equal to 0. Okay. So B is negative 1/3 A. Right? That's going to be positive 1/18. So keep a record of all these things because you're going to write everything together at the end. Okay. And the last one is going to be 2A minus B minus 6C equal to 0. Okay, the constant terms. So I'm going to write it here. Unfortunately, I don't want to go up and down there. So 2A minus B minus 6C equal to 0. That is the constant term. A is negative 1/6. That's going to be negative 1/3 here. To A minus B, which is minus 1/18 minus 6C equal to 0. So in a way, this is equal to 6 times C. This is 54/18. I ended up creating some really ugly numbers here, but that's okay. So we have negative 55/108. Yeah. Oh, oh my gosh, that is awful. Oh. Okay, so what was here before? Negative 1/3. So to get multiplying by 6, right? Oh. You didn't see that, right, online? Sorry about that. So now C is negative 7/108. Still an ugly number, so doesn't help, but is that okay now? Okay, so your general solution y equal to C1 e to the power of 3x. Okay, since I did not change the left hand side, plus C2 e to the power of negative 2x plus this polynomial of degree 2, which is going to be minus 1/6 x squared plus 1/18 times x minus 7/108 okay, times x to 0. Okay. And that is your final answer. So you can see that if you just had ax square as your yp, you would have lost those two terms that came after that. So it's very important that you start with the most general solution. Okay, and if two of them are equal to 0, let it be. That's fine. Okay. All right. So those are the three standard cases. Now ready for some fun? Any questions? So let's see how this can go wrong. Okay. That's number 4. I want you to try this yourself. Okay. I'm going to keep the same left-hand side so that you don't have to recreate your homogeneous solution. So Example 4, y double prime minus y prime minus 6y equal to 3 e to the power of 3x. All I'm doing is changing the value of k. So take your time and try this. What about online? Is anything bad happening? I'm expecting something bad to happen. So something bad is happening, you're on the right track. If you got a solution, you're on the wrong track. Okay, so unless you have seen this before. Did something bad happen to the people online in terms of the solution? Not to you. Yeah, you get weird things, right? So if you try your typical yp equal to a times e to the 3x, okay, then you have yp prime equal to 3a e to the 3x and yp double prime equal to 9a e to the 3x. And you plug it in and you get 9a, then you have minus 3a and then you have minus 6y, that is going to be minus 6a times e to the 3x equal to 3 e to the 3x. Okay. This is 0. Then cancel e to the 3x and you end up with this great result of 0 equal to 3, which you know is not true. Okay. That's not why you are taking this course, to do this. So what should have been wrong here, or what could have been wrong? Your equation cannot be wrong. Okay, the differential equation is okay. The homogeneous solution is okay. Okay, that is where the focus should be. Okay, this part here. That is a homogeneous solution. Okay, that is fine. The only source of mistake here is what? The yp. I mean, that's the only thing we did new here. Okay, but look at yp. Do you see something wrong with what you wrote for yp? Look at yh and yp. Do you see something that you are violating here? Look at the first term of yh. Look at this term and look at this term. Are they really different? They are linearly dependent terms. Okay. This thing and this thing are the same. You're calling this a C1, that's A, who cares, right? So all you're doing is taking the homogeneous solution and trying to plug it into the equation. Of course, you get 0. Right? No magic there. Okay. So this would have been wrong. Okay, so we need to fix that yp. Now, when we did case number 2, what was our fix? We took the solution and did what? You had a repeated root there, which means you had e to the power of r1x and e to the power of r1x for case 2. Yes, we multiplied this by an x and created a linearly independent root, right? Same process here. So the fix would be to multiply your typical guess by an extra x, just one x, okay? Ax e to the power of 3x. Now, do the same process. Now the problem becomes a little lengthier because you have to do product rule and all that stuff, okay? But it's going to work now. Okay? So yp prime equal to a e to the 3x. That's the derivative of x, which is 1, plus 3ax e to the 3x. That's the derivative of e to the 3x, which is 3 e to the 3x. So yp double prime would be 3a e to the 3x again product rule here. Okay. So you can see the problem gets a little lengthier. That's going to be 3a e to the 3x plus 9ax e to the 3x. Okay. And this is the reason why I emphasize on writing the homogeneous solution first, because as soon as you write your guess yp, you need to match it yh and make sure that there is no linear dependence of functions. Okay. So if you don't write your yh, you don't know what's going on, then you're just wasting your time. All right, so let's plug in all these terms into the equations. So we have yp double prime. You can simplify these two actually. This is 6a. We have 9ax e to the 3x plus 6a e to the 3x. Those two are yp double prime. Minus yp prime would be minus 3ax e to the 3x, okay, minus a to the 3x. This part is minus yp. Minus 6 yp. Equal to the same right hand side you had in the problem, which is 3 e to the power of 3x. Now there is a very important step that will kind of help you understand that you're on the right track. Okay, if your algebra and calculus and everything is correct, then these terms should always cancel out, okay, always. So you don't have any illegal terms to compare here. Okay, that's the magic of this process. Okay. The whatever x terms you had here, there was nothing to compare on the right hand side. Okay. They fall out naturally. So all that remains now is 6a minus a, okay, which is 5a, and nothing else on the left hand side. 5a equal to 3. So you get a equal to 3/5. I did not miss any terms, right? 6a minus a. Yep. So don't forget that your yp was ax e to the 3x, not a to the 3x. Okay. Yp is 3/5 x e to the 3x, and your general solution y equal to yh plus yp, which is c1 e to the 3x plus c2 e to the power of negative 2x plus 3/5 x e to the power of 3x. After you write your answer, always in section 2.5, make sure that no two terms are linearly dependent. Okay, this and this, of course, are linearly independent from 2.3. The new thing is here. Okay, this e to the 3x is kind of a dangerous thing, right? But this extra x is going to save you. Okay. So everything is clean, and that is the final answer. Okay, so the key thing here is to multiply an extra x where needed to generate linearly independent solutions. Just one extra x at a time. Okay, don't just multiply x to the power of 10 to be safe. Okay, that's not how it works. Multiply x to the power of n, where n is the smallest possible value to get linearly independent solutions. The key word here is the smallest. So n equal to 0 is not going to work because that's going to make this and this linearly dependent. Okay, n equal to 1 is the smallest one there. If you try n equal to 2, you're going to get this equal to 0, so that's not going to work. Okay, this is the only value that's going to work here, n equal to 1. Any questions on this? Understanding this concept is the key thing to 2.5. If you know this thing, the rest of this is calculations, and you can get done with most of the examples, but make sure that you understand why I multiplied that extra x there. All of you okay with that? Okay, now let's change this. Example 5. So I'm going to change my left-hand side to y double prime minus 4 y prime plus 4y equal to 5 e to the power of 2x. Try that and see what you would do. All of you agree with my homogeneous solution? All of you? Yeah, no doubts about this? Okay. Of course, the right-hand side had to be that function. If it is e to the 3x, we'll be clear, right? It is e to the 2x, so you should be careful. This is how I usually do it. Okay, write your typical YP. Just like how you would have done if there was no issues. That's going to be a e to the 2x. Next thing, compare this with each term in the homogeneous solution. Okay. Are they going to work? No, because this and this term are linearly dependent. Okay, so this is not going to work. So our next choice is yp equal to ax e to the 2x. Okay, most of the time it works. Does it work this time? No, okay, because this is here. So what is our fix? Squared. So no, because these two are linearly dependent. Okay. So y equal to ax square e to the 2x. Now for this problem, it's not going to create a whole lot of extra steps. Okay, instead of ax e to the something, you have ax square e to the, you still have to do product rule, but you know, it's not a big deal. Okay. But this is the key step here, right? Once you get this wrong, you cannot save this. So make sure that you do this carefully. All right, so yp is ax square e to the 2x. So yp prime is going to be derivative of x squared is 2x. Okay, so it's going to be 2x e to the 2x plus 2x square e to the 2x. And yp double prime. Product rule here, product rule here. So it's going to be 2a e to the 2x plus 4ax e to the 2x. Both those terms come from the first one by product rule. Okay. Product rule on this one will give you 2a times 2x 4x e to the 2x plus 4a x square, okay, because of the 2 up here, e to the 2x. So it's a little bit of product rule calculation there, but nothing too bad. Okay, so it's going to be 4ax square e to the 2x. Plus you can combine these two to be plus 8ax e to the 2x plus 2ax e to the plus 2a e to the 2x. Plus all right. Let's write all this into the equation and clear up things. Okay. Once again, if your math is correct, a whole bunch of terms should cancel out. Okay. All right, so yp double prime minus 4 yp prime minus 4, sorry, plus 4 yp equal to 5 e to the 2x. When you plug in all those terms into here, it's going to be 4x square. Just factor out e to the 2x at the end, okay, just to make it more compact. So it's going to be 4x square plus 8x plus 2a minus 4 yp prime is going to be minus 4 times that top term. It's going to be minus 8x, and you have minus 8x square. So this part is your yp double prime. This is minus 4 yp prime plus 4 yp, that is our original guess. That's going to be plus 4 a x square, the whole thing times e to the power of 2x equal to 5 e to the 2x. So does my previous promise still hold true that the terms should cancel? You have a positive 4ax square here, positive 4ax square here, negative 8ax square here. Cancel, cancel, cancel. You have a positive 8ax here, negative 8ax here. Cancel, cancel. So there's only one poor term left behind here. That's going to be 2a equal to 5. So a is 5/2. What if they don't cancel? That means something is wrong. Okay. Maybe something is wrong with your product rule or misassigned somewhere. Okay. So these terms have to clean up at some point. So in this case, n is 2. Okay, that is the smallest value that will bring a linearly independent set of terms here. Okay. So your final answer, y equal to c1 e to the 2x plus c2 x e to the 2x plus 5/2 x square e to the 2x. Okay. Always do a visual inspection to make sure that no two terms are linearly dependent. Okay. Any questions on this? So for the rest of the lecture, what I'm going to do is I'll write down the equation. I'll just ask, or we'll just write the yp. I won't do the whole thing, okay, because I think once you figure out what yp is, the rest is just procedure. Okay, so guessing the yp is the key thing. So let's just focus on that part. Okay. Example 6. So the general question for all these things, all the following examples would be write your guess yp. Okay. Not solve. So you still have to find YH, okay, because we don't know what YP would be without YH. Okay, so find YH, write YP, stop. Okay, that's going to be the process. So let's start with this. Y double prime plus 12 Y prime plus 36 Y equal to 2 e to the power of 6x. What if you agree with the YH part? Just be very careful about what terms you're looking at. Okay, so this is a positive 6x, this is negative, that's negative. Okay, so be careful. Don't just jump and do something in a hurry and waste your time. The typical YP for this term would be a e to the power of 6x. Okay. Does that work? Yes or no? No? What about online? Any opinions? Yes or no? This is e to the negative 6x. This is e to the negative 6x. This is e to the positive 6x. Yes or no? Yes. Okay, no problems here because these are completely different or linearly independent functions. So this is correct. Okay. No need to fix. Okay, if you fix this, it's going to be wrong. Okay, it's not one of those cases where you go on a charity mission or just multiply it by x or x square. It won't work. Okay. Example 7, y double prime plus 12 y prime plus 36y equal to 2 e to the power of negative 6x. Same left hand side. Okay. So don't redo the YH. Okay, that's still there. The guess YP should be based on this one, and then you compare with the homogeneous solution. Okay. Will this work? Now the answer is no, because this and this function are linearly dependent. Okay. So no. You try to fix it once. Will that work? No, because that is linearly dependent with this one. You end up with this, okay, 1x at a time. Will that work? Yes. And when you say do not solve, that means you just write it and stop. Okay. Doing anything further from here is just going to be a waste of time. No need to do it. Because the process is the same. Once you have to YP, just sit down and do the math. Is that clear why I did one for the one thing and one not for the other one? Is it okay? What about this one then? Example 8, y double prime plus 12 y prime. So the homogeneous solution is still the same. Plus 36y equal to 2 e to the power of 6x plus 2 e to the power of negative 6x. I'm adding those two things. Absolutely nothing in this world that is stopping me from adding more terms. So just keep on adding terms. So for now, just 2 terms. What do you think I should do here? You have a sum of 2 terms. What is your instinct tell you? Yeah. Just add 2 YPs. Okay. What's the worst what could happen? So for this, the YP would be a e to the 6x. For this, the YP would be, don't repeat a now, okay, because I already used it here, for something else. So b e to the power of negative 6x. And that is your YH. Don't forget this. Okay. That is the golden part of the problem. Okay. Now, which term or which terms are okay here? Is the first one okay? This is okay. There is no e to the power of positive 6x here or there. Okay. So this one is okay. What about this one? No. Do the same fixing you did earlier. So the correct YP would be a e to the 6x plus bx square, okay, because we don't want clash with either of those terms, bx square e to the power of negative 6x. What if you had another term here, say 5 e to the power of 3x? What changes? Plus what? C e to the power of 3x. Okay. Again, just to be careful, always compare your YH with what you just wrote. No problems here. Okay, so it's safe. So you can keep on adding terms to your YP, and you have to do more math, but otherwise nothing changes. Okay. All right. Any questions up to there? Let's do example number 9. Wow, it's a lot of examples. Y double prime plus 4y equal to cosine 3x. Okay, let's start with some harmless ones. Just write yp. Don't solve for anything. So just to remind you, this is your simple harmonic oscillator. Okay. Okay, so my YH is your typical simple harmonic motion, C1 cosine plus C2 sine. For this function, what is your typical YP? We did that around half an hour ago, probably. Yeah. Good. A cosine 3x plus B sine 3x. And is that good to go? Is there any clash between these terms? No. Okay. That is good. No need to change anything. Don't complicate things which are already going to work. Okay, just leave it there. Now let's have some fun with the same thing. Number 10. Any questions about that example? Y double prime plus 4y equal to cosine of 2x. So I'm keeping the same left-hand side. We don't have to redo the homogeneous equation. So that is my YH from earlier. And this is what you would typically write as YP. Okay. Did I really do anything new in that YP? Do you see any difference between this term and or this pair of terms and this pair of terms? Nothing. Okay. I can call this C1A. Who cares? Okay. So this is linearly dependent with this, and this is linearly dependent with this. Okay. So that YP is completely wrong. How do you fix it?
Inside the cosine to x, so the cosine a to x. I'm not sure.
Oh well. Oh, you want to change the frequency of this?
Yeah.
Well, let's do easier things. Yeah. What would be a better way of doing things compared, just similar to things? Multiply an x to this, right? So fix by yp equal to ax cosine 2x You cannot change the function. You can only do modifications to your yp by multiplying some x to the power of n, okay, plus b x sine 2x. So the important thing here is to multiply both the terms, because otherwise one of these would still remain linearly dependent. Okay. So this as an x, that's an x. You should try to do this yourself. It's going to generate a whole bunch of terms by product rule. Okay. Product rule, product rule. When you do yp double prime, you'll have product rule, product rule, product rule. So 4 product rules. Okay. In case you didn't get enough practice with that in calculus 1, you'll get it here. Okay. But for now, we are just focusing on this. Okay. We will see this again tomorrow with your spring mass oscillations. Okay, this x here and here is going to wreak havoc. As x goes to infinity, you can see the oscillations just go to infinity. Any questions otherwise? All of you understand why I multiplied the x on both the terms? Number 11, y double prime plus 4y equal to cosine of 3x plus sine of 2x. Things are getting crazy now. Again, if you have terms added together, all you have to do is just take it one term at a time and add individual yp's to them. Okay? Just don't repeat any constants, because in general they don't have to be the same. So this would be a cosine 3x plus b sine 3x, and this would be some c cosine 2x plus d sine 2x. Remember that cosine or sine you have to do both. Okay. And your YH is still here. Oh, it's still up there. Am I good to go? Or should I change anything here? Is this term okay? This is okay. What about this term? That's also okay. What about these two terms? Not okay, right? So you have to just look at it term by term. These two are the same as what you have up there. Okay. So this needs to be fixed by multiplying an x to the, or x to both the terms. So you could write as c x cosine 2x plus d x sine 2x. Right. So I finished this lecture by doing a tricky example, which is in your homework. Okay. So I'll change the numbers a little bit, but I'll show you why traditionally that problem has been a headache. Okay. So number 12. So I'm going to do this fully. Y double prime minus 3y prime equal to e to the power of 3x plus 2x. So the right hand side is a combination of exponential and a polynomial. Okay, so nothing unusual there. So can you just start by finding the YH first? It's a Y prime, okay, not a Y there. hope all of you agree with my YH. Okay. C1 plus C2 times e to the power of 3x. Now comes the crucial step. Okay. If you can survive this, I think the rest is just routine plugging in and all that stuff. So typical YP based on each of these terms, exponential function. But now you know that's not going to work because of this. Then you have a polynomial of degree 1. So a polynomial of degree 1. Again, if you have a tendency to write ax plus b, be very careful because this a and that a may not be the same. So just give some other name. Okay. Unless you are very careful about where you take your a's. So first question before we invest any time into this, is this correct? No, because this term and this term obviously are linearly dependent. Okay. So fix. That's an easy fix though, right? Yp equal to a x e to the 3x. Okay. Nothing to do with this part. This and this are linearly dependent, so you need to fix it by multiplying to yp, not yh. All right. Is there anything else wrong here? Yeah. The C and the C1. This is a little subtle. Okay. This constant and this constant are linearly dependent. So it's very easy to miss this and then start doing the rest of the process. You don't know what happened. Okay. So you have to multiply this entire term with an x so that no two terms are linearly dependent. Right? So x times bx plus c. That's the only thing you have to be careful about polynomials, because if you multiply just one term, you're going to create more terms here. Okay. So if you just do bx plus cx, those two terms are linearly dependent. So the only way to fix it is to multiply it outside the polynomial, x times bx plus c. Okay, that way you have bx squared plus cx. Okay. So it's going to be ax e to the 3x plus bx squared plus cx. Okay. Now if you do a visual check, none of these terms are linearly dependent with any of these terms in YH. Okay. This is your golden term, right? No two terms here match any of these terms. Okay. That is the key thing. Now it's yours. Okay. To find yp prime, yp double prime, plug it in. Yp prime would be a to the 3x, product rule here. Okay. 3a e to the 3x 2b x plus c. I've seen students writing bx squared plus cx and then they feel bad and write another d here. Okay. But then you're creating an additional problem because that d is linearly dependent with c1. So please don't do anything artificial here. Okay. Let the math take care of itself. And yp double prime is 3a e to the 3x I missed something here. Yeah. Yeah, thank you. I mean, I'd have been happier if there was no x there, but you have to have it. Right? So it's 3a e to the 3x plus 9ax e to the 3x plus 2b. Okay, so you can now plug it in. So it's going to be 9ax, plug it into the equation, 9ax e to the 3x plus 6a e to the 3x plus 2b. Okay, that entire thing is yp double prime. And then you have minus 3 yp prime. That's going to be minus 3 times this whole term. Okay. Minus 3 times 3 is 9. So it's minus 9ax e to the 3x minus 3a e to the 3x minus 6bx minus 3c. That's yp double prime minus 3 yp prime equal to e to the 3x It's 2x plus 0. Good. Just a placeholder. All my promises up to here are still true. Okay, those terms cancel. And you just have just enough terms to find your coefficients. So you have 3a equal to 1. So a is 1/3. You write down clearly what coefficients I'm comparing here. E to the 3x, you have 3a equal to 1. So a is 1/3. The coefficient of x would be negative 6b equal to 2. So b is negative 1/3. And the constant term would be 2b minus 3c equal to 0. Okay. So c is 2/3 b, which is negative 2/9. Once you see it, it's not too bad. Okay, but the first time you do it, it can surprise you, okay, because of this c and c1 being linearly dependent. Okay. So the final answer, y equal to yh plus yp. Yh is up there. And yp is based on these coefficients, plus a third xc to the 3x minus 1/3 x square minus 2/9 x. After doing all the hard work, don't plug it into the wrong terms. Okay, so it's ax, not a to the 3x, and it's bx squared, not bx plus c. Okay. All right, I know you have a test tomorrow, so you don't have to worry about this right away. So study for the test, and then please do all the homework questions in 2.5 religiously, because everything has something or the other to teach you. So just take your time and do them. Okay. And I have office hours today at noon. If you have any questions for, not noon, actually 12:10. Okay, if you have any questions about the test or anything. And otherwise, please, we'll still have a small lecture tomorrow, okay, around 30 minutes. All right, I'll see you tomorrow then. Yes, around 30 minutes. Yep. So
Thank you.
I'll stop around 8:30 or something. Okay. Yep, thank you.
Would you tell us to use Bernoulli?
Yeah.
Okay.
Yeah.
Oh, yeah, yeah. Okay. Have a good day. See you tomorrow.
Any other questions here, Zay or Molly? Stop the session.